Hey, welcome back. Today we're going to talk about related rates. Now, related rate is basically an application of implicit differentiation. So in last section, you might remember we used implicit differentiation to take a derivative. Recall we took the derivative with respect to x, and this gives us this idea of dy dx. Today we are going to take the derivative with respect to time, or t. So today, our solutions or our derivatives are going to read something like dy dt, dx dt, and we can even get crazy, like if I'm looking for the change in area. Remember, this is the change in my y values with respect to time, the derivative with my x's with respect to time. So I can even look at the change in the area of a curve, or like area of a circle, with respect to time as well. So we're going to have d something dt today. So for example, let's take a look at let's take the derivative of this parabola with respect to t. Well, to take the derivative of y with respect to t, this is just going to be dy dt. To take the derivative of 3x squared with respect to t, now this gets a little bit trickier. We're going to get to 6x. But like with implicits, now we have to take the derivative of x. Now with implicits, we said the derivative of x was just dx over dx, which became 1. But notice, here we were taking the derivative with respect to x. Today, we would take the derivative with respect to t. So we would get dx dt. So today, we're just adding a d something dt to everything that we're going to take the derivative of. And we can do this with a circle as well. For example, here's a circle. If we were to take the derivative with respect to t, we would get 2x dx dt plus the derivative of y squared would become 2y dy dt. Now we're equal to 0. Now remember, we're already used to tacking on the derivative of y with respect to x, dy dx. But today, with respect to t, everything gets a dt, every variable, like dx dt, dy dt, everything gets a variable, and there's our derivative. So a related rate is an application in which we want to find the rate of change of an object in motion. So today we're going to talk about how things change over time. An example. Let's say we have a particle moving along the parabola y equals x squared plus 1. So if I could graph that here, let's do x squared plus 1 right here. We want to find the rate at which the y value is changing when x is 3. So when x is 3, I can go ahead and find that point. If x is 3, y is going to equal, what's that, 9 plus 9 plus 1, which is 10. So we're going to be at the point 310. So what this is saying, at the point 310, we want to find the rate at which the y value is changing. So that is the rate of change of the y values when y is changing, when x is 3 and x is changing at a rate of 3 centimeters per second. So what they're telling us is we know how fast x is changing. Our first step is just to list out everything we are given. Well, we're told x is 3, and we're also told that the rate of change of x is 3 centimeters per second. Now notice these are always going to have some sort of per second. That's a time. And this is a distance, right? So it's a distance divided by time, so this is actually a velocity for us. So, but we call it dx, the change in x, with respect to time. And that here is just 3 centimeters per second. We'll talk about the units later on here. The next is, what do we want to find? Well, we want to find the rate at which the y value is changing. And we talked about this earlier. A rate is a derivative for us. So we want to find the derivative of y with respect to t. Now, the equation they gave us, so every one of these is going to be solved the same way. What are we given? What do we want to find in the equation? So they give us the equation y equals x squared plus 1. This is our position. It can give me my position anywhere on the graph. Next, to find the rate, we are going to take the derivative with respect to time. And I can do that pretty easily. This is going to become dy dt equals, take the derivative of x squared with respect to t. I am going to get 2x, but I'm going to multiply that by the derivative of x, which is dx dt. And the derivative of 1 is just 0, so I don't need to write that. So there's our derivative. Next, I want to solve it. This, I just plug in everything I know. dy dt, oh look, that's what I wanted, dy dt. 2, x is just 3, we told that up here, and dx dt is 3. And that gives us 6 times 3, which is 18. So now let's talk about units. Well, over here they said the distance we're talking about is cm, centimeters. So the change in y, that's going to be centimeters. And the change in time, they're telling me is seconds. So this is changing at a rate of 18 centimeters per second. And that's it. That's all we have to do there. So let's take a look at another example. Given that xy equals 100, find dx dt when x is 2 and dy dt is 6. So they're asking me to find the velocity, that's what this means, the velocity in the x direction. When they give me the velocity in the y direction. So I'm going to write out my givens. First things first, write out everything I'm given. They tell me x is 2 and dy dt is 6. And then I'm going to list out what they're asking me to find. Dx dt. Now this is, again, it's called a related rate because we're looking for the change in something with respect to time. And notice, both of these are derivatives. Like, it's not just find dy dx, but it's find the change in x as well with respect to t. So to solve this, when we look at our function, we have x, y equals 100. This is going to give us the value or the position graph. We just have to find the derivative. So we take the first, multiply it by the derivative of the second, plus the second times the derivative of the first. This is the new one. The derivative of x is dx dt. Anytime I say dt, that's a related rate, dt. And that's going to equal 0. Whoop. That's a weird looking 0. Sorry, that's still a weird looking. Come on, erase, erase. There we go. That should be 0. Now I'm going to plug in everything. I'm going to get x, which is 2, dy dt, which is 6, plus y. Well, they don't tell me what y is, but we can find it out in a second, times dx dt is 0. We have to find the y value. Well, that's not that bad to do. When they tell me x is 6, I know that x times y is 100, but they tell me x is 2, not 6. 2 times y is 100, so y is 50. And I can plug that in right here. And solving it, dx dt, we should get negative 12 over 50, whatever that is. And there's our answer. So what this is telling me is, imagine this. If we're looking at a graph, this is just the function y equals 100 over x. It looks like this. At the point at x equals 2, they're telling us vertically it's going up 6. So they're telling me it's going up like 6 miles per hour, whatever. And horizontally it's going in negative, so it's going in this direction. So there's my dx dt. So we know it's going up and to the left. In this case, because it's negative. This was positive, we're going up and to the right. Or down and to the right in this case. We would have to. So we kind of know our position. So now here's what we know. We know, or we can find our position, which we did. It's at 2, x was 2, 50. And then we also now know its speed in any given direction. Very cool stuff you get to find out. All right, go into video 2. We'll take a look at some more applications.